why are we here? Like, why is everything's been exploding in data centers? Infrastructure has to change rapidly. What brings you here?
Yeah. So I think the infrastructure has been changing pretty rapidly due to the rack densities, right? So I think everybody's heard that we've gone from like a 3 kW rack in the 90s to a 17 kW rack in 2020. And then all of a sudden, without warning, 120 kW rack showed up. Yeah. And I think it's good to talk about the first principles behind why that is. For the entire existence of a data centers are placed on a sort of tier order, right? First of all, if you've heard about the NFL cities for a US reference, wherever the eyeballs are or the people are, right? The end user using that traffic, creating the data.
Right.
Then it's data gravity, or wherever that data is housed. Then latency, how fast you can connect to something. Then wherever the transmission line is or the electron. Now we're talking about the molecule because we're doing on-site generation, and possibly in the near future, the atom, wherever the nuclear power might be.
Okay.
But the reason behind that is the first two pieces, the people has been for a while. Then we've got data gravity centers wherever the businesses are. And latency has not really been a big driver around that. Because data centers being, if you put a data center somewhere, you have a 2 kilometer distance that you have to put it close to when you link them together. Otherwise, you make a latency hub. And that latency hub has worked out great for the last 30 years in using the TCP IP protocols.
Because humans are relatively close to where that needs to be, right?
Yeah, and it just worked out. And what has changed now is the type of workloads. We started using these large language models, and the large language models needed to link a lot of things together. So in the past, you'd have a data center, 20 megawatts was a big deal, and they fill it with a couple thousand racks. And they're all working different workloads or different waves in the ocean. What's changed now is that 20 megawatts is all running the same workload, and it has to talk to each other. And when you do the talking to each other, the packet loss becomes significant. In the TCP protocols, you could have packet loss like you're lagging on the media or like Teams or Zoom.
Or gaming, right? Gamers are super sensitive to that.
Yeah, it's really frustrating when someone comes around the corner and gets you.
That's right.
Just because of lag.
Yes.
That ping rate's important. But going to a latency sensitive thing is when you're breaking up that puzzle over 1,000 different GPUs, if you were to lose one of those packets, it actually causes you to go back to the checkpoint and slows down the training.
Yeah.
And you can monetize that. If you can think of a 20 megawatt cluster, 10,000 GPUs of H100s, and then $2 an hour, that's about $3.4 million a week.
Okay.
If you're an infrastructure as a service, and up to $15 million a week if you're software as a service, that you're losing revenue if you have to keep going back
just on packet loss.
Well, just on slowing that clustering and that packet loss, slowing it down for packet loss. So in order to solve for that, they had to go inside the 1 meter boundary, and that 1 meter boundary of copper collapsed 9 racks of GPUs at 8 Ps and put 72 into one rack. But then you lose the fact that you can't put a heatsink in there because 1.8 meters high or 48 RU high, 600 millimeters wide, 1,200 millimeters deep, you can't fit 72 GPUs with their heatsinks.
Right.
That created liquid cooling.
Right.
We have to further densify that. And for the last X years, we've been, as an AC appliance, converting to DC internally. To make space, we have to actually remove those electronics to the side, and that's shifting to direct current to support the packet loss specifically.
All right, I want to unpack two things because I think they're different than our conversations used to be. So liquid cooling, in most conversations I was in, is about efficiency and about heat rejection of the chips and the rate of the heat. But what you just said is space, like physical dimensions was a major driver. And I think that's missed in the conversation.
Yeah. The thermal efficiency is useful, right? Because you went from a 700 watt chip to 2700 watt chip with the GP200s from the H100s.
Right.
But in particular, it's the closer the chip can be together, the more efficient it is, which means you have less loss and wastes associated with it. That initially drove the thermal issue, and that's why everybody was talking about that. But the underlying first principle was packet loss and making sure the cluster could talk to each other more efficiently so it didn't go back to checkpoints. And that's causing the same thing
on power.
For power, right? So because you have to densify that, to get that power delivered, first of all, you have to disaggregate the power electronics, but then like you need to up the voltages to 800 volt DC or plus or minus 400 in order to get the power delivery in a form factor that's utilized for that chip or for the chip in the rack. Because the other piece is you can't end up showing up like a really complicated space. If you ever walk into the old IT closets that were just like a mess with the fiber.
Sure. Yeah.
You couldn't ever work on it because it was congested.
Right.
And that's what's happening. You're going from like 2 whips to 4 whips to 8 whips to 16 whips of AC. And just, you can't fit that with the fiber going from 4 home runs a rack to 16 with the 8 GPUs to 144 with the 72 GPUs.
Right.
All the way up to 288 and beyond.
On the 144s.
Yep, on the 144s.
Yep.
So that's a congestion constraint. The power is a congestion constraint, and the thermal is a congestion constraint to service the rack. But the underlying principle is driven by the network protocols and not having packet loss.
Interesting. I think that's a totally different approach for this conversation. Like for why people understand, somebody watching this podcast, why they understand or what they think the drivers are between things like liquid cooling. And even, as you mentioned, power changing, like a lot of that is a discussion around efficiency. So I want to unpack that a little bit later. We'll get into like technical, like what's driving that, where the bottlenecks are, and then what we think potential solutions are. But you just unpacked like everything from the user side all the way to power generation in your explanation. Tell everybody who you are and why, that's a lot of different verticals of the industry to have great grasp of that you actually put together concisely. Where did you start in this industry? Who are you?
Yeah, I have a checkered past, right?
Right. But first, just what's your name and what's your title? What do you do right now?
JP Buzzell, data center chief architect for a company called Eaton. Right now.
Small little company in Ohio.
Original equipment manufacturer, an OEM in the industry. They can provide anything from the grid all the way down to the chip. And then additionally, a lot of the hot aisle containment, the metal, the basket tray, everything associated with that as well. I've been with Eaton 9 months. And I've been here the last 9 months focusing on direct current power, largely because a year and a half ago now, I realized that I needed to solve that because I couldn't build my next cluster. I started as a nuclear operator, like a lot of people in the data center industry, did the Navy thing for about 3 years or 12 years, 3 years of which underwater.
Shout out to our Navy nukes, which there's many of them.
Many of us around here.
Yep.
And then I got in the data center industry by happenstance.
Like most of us, like myself included.
Yeah. My mom didn't want to move in with me because I was supposed to, she's supposed to move in with me. And then my wife said, I want to live by family. So I was like, I guess I'll call the artist formerly known as Facebook and go build data centers.
Interesting.
So dirt, level 1, all the way up to level 5, commissioning, took them over operational, had the opportunity to go over to the site ops side of the house from FAC Ops and, help out build the first 5100 GPU cluster there.
Wow.
After that, I went to Oracle Cloud Infrastructure, director of operations for the Ashburn cluster while they were scaling out their infrastructure. I built their first 4,000 A100 cluster there, scaled out that, and then the company asked me to go over and fix their design team for data hall design. So there I, grew the team from 5 to 60 people in about 3 months, and then I had to 100x their design throughput to meet the demands.
Is that an unusual pathway? Like, I don't know that you get a lot of boots on the ground, like experience and pathway up to building out the design team and essentially the philosophy of how that design team is going to operate.
It might not be it's traditional. It just seemed like sense to me because once again, Navy nukes, you're trained. I started off as an electrician in the Navy. I got all the Pokemon. So I qualified from electrician, auxiliary electrician aft, we call it in the Navy, all the way up to engineering officer of the watch, engineering duty officer, quality assurance supervisor, master training specialist. I ended up teaching nuclear power for 3.5 years. So in the Navy, you're taught you have to learn it, touching it, and then you have to then go operate it, do the maintenance, and then teach it.
So for you, it made perfect sense. This was how you had already operated.
Yeah, I was a manager at a nuclear plant. I was like, well, I guess I'm gonna go be an IC first. I went and found a greenfield site where it was still dirt. And I went through all the initial owner training, and it was the plan to learn that stuff.
Yeah.
Just to keep going through there, right? So it made sense to me. I think it's maybe atypical, but it just, I didn't know any better.
Right. That makes sense. Okay, so then you're Oracle OCI, you're building out clusters, you're leading the design team to fulfill the new demands.
Yep.
Then do you hit what happens? Am I missing something there? Or do you hit a bottleneck at where you were at Oracle?
Well, yeah. So I was at Oracle, working on this Abilene project, right? It's what supports Oracle supporting Stargate and OpenAI there. And we did the design for Stargate in about 6 months or so. And, completely created liquid cooling, how to do the new hybridized network infrastructure. Pradeep is a great guy. Mahesh is a great guy. Jag, love working with them. But then you realize that I can't design my next cluster without power delivery. And I guess I maybe couldn't articulate well, but I couldn't get figure out how to communicate the urgency to the OEMs. So I ended up founding Eaton so that I could come help drive that based on Eaton's legacy of power distribution, solid engineering practices. And that's what got me here.
So you're at Oracle, you're ready to build the next cluster, but the market doesn't offer what you see as the next need to build the next size cluster, the next need.
It doesn't. And then it's also a different piece of like the discipline for it, right? So once you get past probably a 4,000 to 10,000 GPU cluster of H100s, once you get to a 30,000 GPU cluster, which we deployed and built of H100s, and once you're getting that design, it gets very sensitive. And the analogy I use is the light switch in your house is the same light switch in an airplane cockpit, and it's the same light switch in a nuclear power plant. Just the nines of reliability is different, and how it's maybe constructed or the QA/QC from going into it's different. So I can have a little bit of failure rate with the light switch in my home, worst case, right? And the TCP IP protocols allowed for packet loss. I can have a little bit of failure because that's the whole thing is you reroute the backbone packets, you might send different ways, it can get in different speeds. In the worst case scenario on Teams, you'd lag, you turn into a robot. Right? So like that protocol makes sense. And like the level of discipline to install the light switch in your home and the type of training you need to do that is a different level of quality than the airplane cockpit with 9 nines of reliability.
Sure. You're speaking my language now.
Yeah.
I'm from aviation, but yeah.
Oh, you're from aviation. I didn't know that.
Yeah.
Whoa, that's cool. All right. So okay.
Well, so I just got done giving a tour to a bunch of high school students. What I was sharing with them is like most people in this industry aren't originally at this industry. Most of us fell into it because it wasn't an industry like it is today 10, 15 years ago. It wasn't the industry it is today 2 years ago, but definitely wasn't 10, 15 years ago. So coming from the aviation side, I learned systems, right? So it's a combination of mechanical systems, electrical systems, information systems. And so at the time, though, this is back in 2007, major Q4 of 2007, major recession, all the airplanes stopped. So my value to the market went way down. So I translated that into power generation. And that's how I found the data center industry. So just moving from systems and aviation and the criticality of those systems, which is what you're talking about 4 nines, 5 nines, whatever it may be, that all resonated with me. So I was like, I can just apply the principles that we use in a mission critical environment, in a different type of mission critical environment.
Yeah. So an underwater airplane is a submarine.
Yeah.
So it's the same, right?
Yeah.
Like it's a system level thinking and design is what matters. And I'll flip over to an aviation example, right? So airplane in the cockpit versus the light switch in the space shuttle.
Okay, yeah.
Right? So let's talk same language here, right?
Sure.
That the level of quality for an airplane cockpit versus the level of quality for a space shuttle is different delta, even though it's the same thing.
Yeah, we're in the aerospace realm.
Yeah, aerospace rail.
But the roles and jobs and criticality are very different.
Yeah. So it's similar to a cluster, right? So if you have standard compute with storage,
right,
that's like the light switch in your house, right? You can have packet loss. Worst case, you go in and you swap out a hard drive or something like that.
Sure.
But then the level of rigor and craftsmanship to install what you do in an airplane cockpit, because of the criticality nature, or a space shuttle, it's much higher. And like how you do that bend of the fiber, it'll pass the light shoot test, but it won't pass a GPU cluster because you get too much jitter. Or if you walk by, you'll literally disturb it and you'll have to go back to a checkpoint. Or the dust in the atmosphere will cause more link flags in the pluggables associated with that, right? So like the same thing happens with power and all the other systems. It's much more systems engineering and they're interdependent.
Sure.
And that interdependency really matters.
Yeah, I think so. I mean, I think that's the evidence we're, here at OCP Global Summit, and all these are, I think what draws people to this is that interdependence, right? This is a great ecosystem to bring those pieces and parts together and talk about common challenges. I want to talk a little bit of that, but so in your own path, you moved from, and I think it's logical, like how you described how it works in the Navy. And so I'm going to know how it works. I'm going to operate it and eventually move to training it and explain it. That's why you're excellent at explaining it. Why then move on from Oracle? You saw a problem to change, but Oracle's under incredible success right now. They're doing lots of things, but it sounds like you have a drive. You're very passionate about this. What drives you to go leave a seemingly great situation with people you love to work with and go solve the next bigger challenge?
Well, I think it's just, if you look at the overall ecosystem, right? It's an ecosystem challenge. For me, the happy answer I try to share is that, it's all about the human connection, improving that human connection. My mom got an AI inference hearing aid upload to her hearing aids, same hearing aids, just improved quality, and she was able to hear her grandkids again.
That's great.
Right? So that human connection, but beyond that, medical advancement is something that really drives me, right? So the quality of care that your parents might get, you'll get, or your children is really going to be unlocked by these GPU clusters and eventually the hybridized quantum GPU clusters. I look forward to the day where I have a thumb drive. I walk into a doctor's office, I plug my medical records in there and check that out. The doctor gets that AI-enabled portion. I can get custom prescriptions 3D printed for me. I pull it out and I own my own data. And in order to get that, for me, I want to need to get it as fast as I can because there's medical things that I want done for my family, and there's certain very deeply personal drivers for that. And leaving Oracle was a really hard decision, to be honest. Like the people's great. I love them all, right? And they're really like, they're answering Dr. Harari's question. Like the reason why I joined Oracle specifically was, if you know what Dr. Harari's question was, is will the future be human? And his thesis was whoever owns the data and has data sovereignty will determine the future of the human race. I'm partial to Oracle, of course, and Oracle Red Bull Racing, but but they're creating a data plane that is just as secure as a government cloud that's open to the public.
Mm-hmm.
And you can do Alloy and DRCC regions so that you can have your own determined cloud.
Yeah.
Right? So like New Zealand got an Alloy region deployed. It's their own hosted cloud within their sovereign borders. Right?
Yeah. Increasingly important.
It's super important. Yeah. Right? So like that's answering a direct need to the market and they're being recognized for it. Right? And I'm super proud of the team. I'm super happy for the team.
Yeah.
But for me to get to the next cluster with what I need when these AMD 400s come out and beyond, the Vera Rubin Ultras and beyond, in order to do that, I need a DC architecture to support that.
Yeah.
So coming here and driving it at Eaton and, driving that path is very important to get that up to the next advancement. And then who all knows what next after that's done, right?
Sure.
Maybe go build another cluster. Who knows?
Excellent.
I think that's why OCP is so important.
Okay.
Right. So OCP is that neutral playing ground where everybody can come together and work together and solve hard problems, right? So the DC shift is a major shift in electrical topologies.
Yeah, let's unpack that a little bit, because I think you and I have had multiple DC power conversations. I'm close and familiar to it, but to me, and why I'm so glad you agreed to join the podcast is, like, I think a lot of people don't know this DC. Well, I don't think they're as aware of the power problem that is pending, that some are bumping up against, but is pending for a broader part of the market. And then this interest around moving to a direct current architecture for compute. Like, there's been the announcement of Mount Diablo, which is converting AC power to DC power. The sidecar you talked about, moving power out of the rack and next to it. You kind of gave us a preview of that. That's one path. But then there's an interest of DC. Why DC? Why are we going to direct current?
The direct current, we heard about the efficiency piece, and you get maybe a 30% benefit for watts the token.
Yeah, like, DC conversation isn't super new. Like, some people are like, well, I don't have conversion losses, which are in the 10%-ish range, right? Depending on how and that's been talked about. But to recoup your investment on up maybe 10%, 8% conversion change, and you have to change a lot of things, it didn't really seem like the market responded to that. Like, there's not enough meat on the bones, but that's changing.
What's changing, I think, talking about before, but going back to the network, you have to disaggregate the power electronics in order to support the compute density.
Because you have to fit all the compute in that rack in the physical dimensions. And right now that's being occupied by power shelves and battery backup units and conversion, all that.
And the big change here is you go from, you've got your dishwasher or your refrigerator. It's an AC appliance in the house.
Yep.
All the racks are underneath the protocol of an AC appliance less than 1,050 volts.
Yeah.
And that's all well and good. But as soon as you transmit DC power from one appliance to another, you now become into DC distribution.
Okay.
And since you've pulled that switch, it's more efficient than to do the full MVSST, and the higher power densities required.
Okay.
Higher the voltage, the better for that. But it's really the network compute density that's driving that fundamentally.
So why can't I just, well, I guess we have power conversion. We have components, right? That would occupy the space. So what if I just moved my step down into the sidecar, and, doesn't that solve it for me?
Well, it does solve you in the interim, right?
Okay.
Like, if you do the sidecar, that gets you there. And
Right.
I expect the sidecar most likely to be utilized in all of the architecture that we have.
Sure.
And like, if you are going to be an enterprise customer that maybe needs like 5 or 6 GB200s or Vera Rubin Ultras, you'd use a sidecar situation surrounded by the rest of your compute, surrounded by your storage. Makes sense.
So you can leverage the existing infrastructure. We're not changing anything in the building to do this. We're bringing 415 or whatever it may be, AC power from the wall into this so we can solve for this density issue.
Yeah. But then the next question is, then why do this MVSST thing and do a full DC distribution?
Right.
That's really where it becomes an efficient deployment. And also it comes down to the density. There's a 600 millimeter wide, 1200 millimeter deep, 1.8 meters high DC sidecar that takes physical space and is a distance between one rack to another.
Okay.
Being able to make sure that it's as close as possible is important.
Yep.
For the compute and the network topology, so the cluster doesn't slow down.
So we really just moved the problem out of a layer, like inside the rack layer, still a distance issue. Now we've just moved it to the rack scale distance issue.
Yeah, like, once you go outside those clusters, once you go past, a 10 megawatt cluster, you're really getting into, you're literally calculating your layer 0 to layer 2 distance protocols, and you get locked into actual fiber distance between L0 to L1 and L1 to L2. And if you exceed a certain distance, you're literally limited, the speed of the cluster is limited by the speed of light. And once you're in those protocols, even if you get a little bit, one set of racks that are like 50 meters versus 40 meters, it's actually will be a noticeable performance difference. So, which
then slows down the whole cluster.
Exactly. And it gets back to the quality and craftsmanship by which you build something like a space shuttle. A space shuttle is designed a certain way to support those compute clusters. And like then you think about efficiency on top of that, and like the medium voltage to low voltage transition using an MVSST, medium voltage solid state transformer.
Yeah. Not everybody knows what that is.
Yeah,
I know that's in your world.
Yeah. So I'm terrible at it. So you then will allow, you can do that distribution, and then you can go to a modular solution. Because I think the other macro trend that's challenging the market is you have a population just based on the fact that birth control was instituted in the 1960s, and you had a population dip of Generation X after the baby boomers. The baby boomers by 1930 will be, by definition, retired in the United States. Might be varied for the different countries. And then you have a industry that's gone at least 10x. So you have a labor shortage from human capital in retirement. So
we're at that at the end of the decade.
Yep. Knowledge transfer issue. And then you have on top of that an increased demand for the workforce, in which skilled trades haven't been focused on as well.
Sure.
So how do you solve that? Right? You can solve that by modularization and taking a lot of the level commissioning offsite. So by creating modular units in an MVSST transformer that's a shippable unit, connecting to a compute module, that then solves for that solution.
What you're describing is we're, from a labor perspective and a skilled labor perspective, you're eliminating how many terminations on cables and how many connection points and how many torque points and checks and other components that have failure rates.
That happen offsite or on-site, it's uncontrolled. If you can do it offsite in a factory setting, and it's really the dust, right? And the cleanliness controls, that's a controlled setting. If you can get to level 3 offsite, ship it. And then that then supports the industry for doctor revenue, right? Because it's all about speed of the clusters right now. That's what the industry is wanting.
Sure.
So getting to the modularization in that aspect, you can plug it in, and then it minimizes the amount of labor on site, right? So I love Abilene. It's sometimes described as the Martian landscape. Right? So it's not really built out yet. So you're transporting 4,000 laborers, or and I like to say master craftsmen, because the pep talk I'd give whenever I was directly running a cluster, I'd show up at 6 a.m. and say, hey, you're building a Sistine Chapel, you're a neurosurgeon creating a positronic brain. That's the level of detail and craftsmanship you need to do that precision. So like you have master craftsmen coming out, and then is it easier to have 4,000 master craftsmen in a centralized location in whatever country you're in, or have them having to be transient from a human capital, from a capital expenditure, because you have to pay per diem for that. You have to pay, transit back and forth. It's a lot more efficient aspect. And I know I'm getting a little bit off.
No, you're good.
But going back to that MVSST, to the driving that point is, getting that form factor allows you to densify better.
So we can densify better. Like you wave a magic wand. We're converting medium voltage AC to 800 volt DC in the yard of the data center?
Or right up against the cluster itself, right? So you have in the yard, you can have an outside transformer. It can be inside, depending on, that's a feature based upon the geographical region. Like if you're in, Michigan, a feature might want to be having enclosure when you do maintenance because it's really cold. But like in Phoenix, it might be more temperate climate there, so it'd be okay. But the feature piece, you have that there in the yard. And then attached to it, you can pipe the DC power straight in and then power the clusters.
And then the clusters, and I saw we have some of it here, like the example of the MGX wall, and we already have some 800 volt. They've announced a partnership with companies like Texas Instruments and others, and Eaton, of doing power conversion in the rack, right? So now, or I would say, what's the right terminology? We're moving from 800 volt DC or 400 plus minus DC power, and we're moving it to 48, 50 volts DC.
Inside the rack,
So we're just doing a step down inside the rack.
Correct. And it stays up, it takes less space. And it's just a function of how do you actually deploy that. And that's what's supporting the cluster. So all of this massive portion is to support the training. But then it's going to transition to inference. And that still is going to be needed, right? Because the higher nines of reliability, I might even assert that 5 nines are not enough for some inference things.
Interesting. Because you think about it, like what I hear from the hyperscalers and those driving is like on the training side, like I think it was Llama 3 when they were first training, like the failure rates were like 10 times a day and it costs like 40 minutes every time, something like that. Mm-hmm. So like to me, that's dollars and cents. So those are very expensive models to train.
Well, yeah, up to a 40% failure rate of GPUs on initial install. And then when you're actually doing the checkpoints to what you just stated is a very accurate statement. But that's training. But then I go into, I'm using this inference cluster.
So I get it on training. Like the value makes sense. Go on inference. Like
But then it's like, training is like you're the architect building the blueprints.
Sure.
Inference is like you're the GC building the house.
Yep.
Or you're the heart surgeon doing open heart surgery with an AI-enabled cluster. That probably wouldn't be a good idea if it didn't work.
Yep, that makes sense.
So like that's where more than 5 nines reliability might be needed. And like that's not absurd because you came from aviation, mentioned earlier, right? So 9 nines of reliability in aviation is a thing.
Yeah.
So if you can be flying, my friend Peter Bach uses this analogy, right? So if you can be flying in an airplane, drinking your beverage of choice without a care in the world, with a full expectation that you're going to land. Right? That's a marvelous thing.
Yeah.
Imagine you can apply that same level of discipline to an ER operating room.
Sure.
Or self-travel or whatever medical advancement you would need that you want for a better quality of care, for a better life in your retirement, or mitigating certain issues that then allows those people to be productive and contribute to society.
Yeah, it's interesting because I think it's easy, us being on the inside, I would say the industry side is like, what jumps in my mind is like, okay, well, the people who are building this are spending a lot of money on trading, like that's expensive. But all these things are going to enable things that are far more expensive to do than even data center infrastructure, like medicine creation, right? And research on that. Like, okay, if I have to wait an extra month to get this output out of the system that I'm using inference for, that month might cost many lives and dollars and cents.
Yeah.
So I think but most people's inference interaction right now is ChatGPT and Gemini and Llama and those, right? But we're not yet seeing the real value of inference on things that are far more valuable than a text chatbot.
Yeah. So student of history, right? If you think back to electrification in 1890.
Okay. I love this.
So if you actually look at Armand's study for data center growth, if you look from 1880 to 1920, it's about the same graph. And after 1920, it goes logarithmic.
Yeah.
But the initial applications for Thomas Edison, he was the magician of the park because he lit it up. Like Llama is like using light bulbs.
Yeah.
For electricity. All the other advances that will come beyond it, I don't even conceive of right now.
Sure.
I'm hoping
because we're still on this part of it. We're still in light bulb territory.
Yeah. So electrification.
We haven't hit the curve yet.
Yeah. Like I was watching a study about dishwashers and electric dishwashers, how revolutionary they were.
Really?
Right? Yeah, because it used to be the most time-intensive thing, along with laundry,
right,
for people who are working at home.
Sure.
Right? So like Monday was laundry day.
It was your whole day.
Yeah, whole day. And actually getting an electric device that can do that has made my life better.
Sure.
Because I can go in there, put my laundry in, hit the button, walk away, come back an hour later, swap it out, opposed to literally hand cranking something for an hour.
Yeah. That can't be interrupted because then the water gets soggy and smelly and your clothes come out and you don't dry. Like you're committed. Like you're not like going to catch a Zoom meeting while hand washing clothes. Like you're not going to interrupt. I know I have like parallel universe 2 timelines, but it's not possible.
It's not. So like it's just what is next after Llama?
Yeah.
Or after the light bulb utilization phase. I think there's some incipient things. And like I shared, my dream, right? Like where I really see is a reality where you can have your own data, right? You can have the right to be influenced.
Yeah.
And then you show up to wherever. If you want some custom Nike shoes, you show up to the Nike shoe store, they scan your foot.
Right.
They 3D print your custom shoes right there. And it's all ran by a robot or, certain aspects of it, and it makes it, that much better. And once again, that's still not much better than a light bulb analogy.
Yeah.
Because I had not yet imagined what's next.
Well, yeah, I think it's easy to like create a dishwasher in your mind, right? From history. Like you can see that you're just replicating. Like I heard one recently, like same student of history, like been doing more reading on the Industrial Revolution and like the good things and bad things that came of it. And how are we going to be prepared for like job displacement, things like that. But the one that I think surprised me the most is factories. They were using electrification was like the backup. It wasn't until they changed the lines, because the assembly lines of using steam energy versus using using electricity, you can do totally different things with these lines because of the infrastructure that needs to be there. And it wasn't until the line changed that actually we saw output progression and efficiencies and advancements in manufacturing. It was really just it was a backup. It was still a light bulb.
Yeah. And it's just, we're at that phase.
Yeah.
So I'm pretty excited what's next.
That's cool. I like that analogy. There's a lot of light bulbs still. I think there's a couple of the backup machines, like where you think about, okay, shoes, like someone makes those shoes by hand mostly or machine assisted. I could maybe 3D print them, but that's going to be for a while, seemingly the boutique version. It's going to be the more expensive. It's going to be not appealing to everybody for a while.
Yeah. So the closest thing that I've seen, right? I have a friend whose son is in the valley working on seeding clouds. And he basically uses LiDAR and then AI to determine when to seed the clouds.
Wow.
So this whole portion, and like he was able to actually give demonstrated snowfall to Utah to increase it by 300 inches, right? In certain cases. So like it's crazy where like you have that LiDAR and what his limitation is, like having that LiDAR and doing it as an inference, it costs a lot of compute and figuring out, because cloud seeding is like, we have the technology to seed it,
right?
But we can't read the clouds well enough to know it'll be effective or not.
Yeah. I can't tell you what it means. I can see it, but I don't know what to do about it necessarily.
Yeah, so it costs a lot of money, and like you have to get a lot of instruments, maybe even some satellites. But then like using LiDAR technology, you can use an inference with a cluster based on all the information. And that might be, but once again, it's not fully vetted out, but like it could be one of those like next after the light bulb utilizations. Imagine you can direct water to where there's a drought for crops, right? Or you can make sure a forest gets enough moisture so the likelihood of a forest fire drops.
Interesting. Now we're talking incredible value.
Yeah. The huge thing. Like imagine if you didn't have to do smoke. You know, smoke inhalation in the Bay Area during the forest fire season.
Right. Yeah, that is incredible value to society. And I don't mean value just in the monetary sense. I mean value, true value.
It's very sad to hear when like people's homes get burned down.
Sure.
And like there's a huge cost of a human cost beyond the dollars and cents, because for me, why I do what I do is it's for the human experience improvement. And how do you focus on that?
And think of the things that it just displaces, like firefighters and the roles and jobs. Like what can we do with our time if we don't have to solve these other challenges? Right. Or respond to these other challenges. So I'm completely on board, completely aligned with you, like all these things that could happen. So back to the power issue. If that's the bottleneck, why can't we do it tomorrow? Like what's standing in our way?
Yeah. So I think right now the biggest voice everybody's going to say is regulation. Right. So that's been a lot of my life for the last 4 months, and even more than that, in talking to different regulators. Right. So we were really successful in going and talking to UL on September 24th. They hosted a summit where we invited major hyperscalers, the major OEM manufacturers, and UL. And we just got the initial minutes that will come out probably publicly in a little bit, but that they've aligned to accelerate the standards by embedding with OCP. In addition to that, the next week, September 30th, October 1st and 2nd, you came and hung out with me and we co-presented to that group. It was the president-elect of IEC, IEEE, NFPA, Train, Carrier, and then also the major OEM manufacturers of the electrical side to talk about how you do that in the IEC world.
Yep.
Both of them have rogered up and said, hey, we're going to make a low voltage DC subcommittee and then embed that into the power distribution work stream that OCP has kicked off this week.
Yep.
And since we'll embed the regulators with us and the industry experts and the actual customers, we're going to be able to move a little bit faster together.
Excellent.
And like the key is that I've noticed that, as you notice, I've moved around to different companies and different aspects of it. Everybody wants the same thing. To be honest, UL and IEEE wants the support as soon as possible. Right. Same thing with NFPA and everyone else. It's just a function of they didn't know who to talk to.
Right.
So it's oftentimes problems if you get everybody in the same room and you just talk it out. Yeah. Oftentimes it's a communication or terminology, right? If I go to the Midwest and I ask for a pop, and I go down south and ask for a Coke, I'm still asking for a soft drink.
That's right.
So,
well, speak on terminology just briefly. So define low voltage DC for this ecosystem, because I think a lot of people listen to this and watch it come from what they think of as low voltage DC is like 48 volts, DC like 12 volts. That's low voltage DC. We're talking about delivering power infrastructure bigger. We're still calling that low voltage DC?
Yeah. So current OS and then the international standards defines low voltage DC as anything less than 1500 volts.
Okay.
So it's a little bit different, right? Because it's just the order of magnitude. We started initially calling it high voltage DC as an industry,
right?
Because it was higher than anything else we've been using before,
right?
And I think it's a function of like getting that terminology together, agreeing on the different voltage levels, because that's key. Because then we can agree on interoperability.
Right.
Right. Because like eventually, the Suez Canal is going to close for some reason. There'll be an ice storm in Minnesota and you can't ship the thing. And someone that's actually trying to bring on a data center isn't going to have the thing they need.
Yeah.
And they need to have the interoperability with the electrical and mechanical groups.
Right.
Like they have the interoperability with the fiber infrastructure.
Yeah.
Right. So
that's a good parallel.
So like, that's the type of level of discipline we need. And it's such a big solve. There's enough for everyone to go around.
Yeah. I heard that just speaking with people at Eaton when we were at your headquarters with the current OS group, like it seemed to me that everybody there agreed. And you had the major representatives from all the OEMs that build power infrastructure for transportation, everything that's electrified in the world.
Yeah.
And they said that this problem of changing the power density of a data center and moving it to DC voltage there's more than enough that any one company can serve.
Yeah.
And they all seem to agree on that.
Yeah, I think all the OEMs agree. I think the customers agree that they need it. And the regulatory body also is willing to support.
Yeah.
Right? So if you imagine like the Hoover Dam, right? The Hoover Dam took 7 different companies to build it.
Yeah.
And it's just a function of like that. Once again, student of history. If you work together and you're open and honest and transparent,
yeah.
And granted, like obviously you want to have co-opetition.
Sure.
Right? Because you want to make sure that we're pushing together. We're making it.
And you guys all have different value propositions. You do certain things differently. Yeah. You have different approaches. We should keep those.
Yeah. But ensuring that you have interoperability, that like I can plug in a MVSST produced by Eaton into a Schneider switchboard or a Vertiv CDU is important.
Yeah.
And the fact that you can create that modularization offsite, bring it, and it's a value to everyone else. And that's why, once again, OCP is a great form for that because it's a neutral body.
Yeah. Well, let's unpack that a little bit. So you described the problem like we need to move to standardization. Regulation is a big piece of that. Current OS, it works on DC microgrid. That's a separate organization that you were involved with.
Mm-hmm.
But they have a committee around data centers specifically because it's such a driving force in that community.
Yep.
And then we have the Open Compute Project, which you stepped up to co-lead power distribution within OCP because there's a lot of interest around this within our community. How do you see that going? Where do we stand with the project? What are we aiming to do with this project?
Yeah, we're kicking it off, right? So the intent right now is we're going to produce a white paper, target Q1 2026.
Okay.
so that we can get an initial white paper out there of where we want to get in interoperability, what standards need to be applied, instead of waiting to then let that trickle out to the UL, IEC, IEEE. We're actually inviting them in as part of the process.
Okay.
And they'll be inside that fellow travelers, as we call it, right?
Yeah, yeah.
They'll be fellow travelers on the process. And since they're going together, you don't have to worry about context load.
Yeah.
So once we get that, we're going to all learn the context at the same time, all decide what low voltage DC is as a group, define taxonomy, define definitions, and then that can be transferred directly into the standard bodies. And that's phase one.
Sure.
Right? Beyond that in power distribution, there's still active harmonic filtering that's going to be a challenge, load step that's going to be a challenge as we continue to scale out the grids. And that can be other things, but right now the most immediate problem that we're trying to solve is low voltage DC.
Excellent. And then that opens up a bunch of other opportunities, right? Like you mentioned the regulatory, but we're also going to have the voice of your co-opetition, right, in the industry, along with potential end users. We have interest from hyperscalers and neoclouds around this problem as well, all the builders. It's fascinating. Once we get something down on paper, there's also rumblings of like other opportunities, right? So once we agree on terminology, taxonomy, as you described, like things like battery energy storage, that's like a major unlock, right?
Yeah. Pivoting away from the direct current conversation. In general, if you look at the topology, you have a GPU cluster that's causing waveforms, and those waveforms move up and they have to be filtered at first with an active harmonic filter to do the first smoothing. And then you get to a battery energy device or an energy storage device, to be more general in that aspect. That energy storage device can then mitigate more of that waveform, right? So if it's a UPS or an NVSST, it can actually take in the waveforms and further reduce that.
And right now we do that. It's compounding the issue. Right now we do that in the rack or near the rack, again, competing for space.
Exactly. You're using capacitors and you're burning power in the rack just to maintain it smooth.
Yeah.
So once again, another reason to disaggregate because you be more efficient overall.
Yep.
And then you get to the battery energy storage systems at the medium voltage level as well, right? So you have all those things, and it's more of a stepped approach in order to do that. And then you also have the load ramp, right? So like, say, hypothetically, the grid gets a hit and the 27 relay or the under voltage relay in your main switchboard at the low voltage sees 3 under voltage triggers in a 1 minute period, indicating a brownout based on the reclosers, and everything goes to gens.
Like it did in Northern Virginia a few months ago.
Exactly.
Okay.
At that point, it's like the grid operator is like, hey, where's my power? I need to get back as soon as possible.
I got to put this somewhere.
Yeah. Like, because it's an actual generator, and when you unload it, because I've worked in the generator field there, like literally it's moving the power factor, and like it's causing significant churn to the grid.
Yeah.
Luckily, the East Coast grid's so big, we didn't have a Spain event. Right? So, but then as a data center operator, when I was the director of operations, like, I'm not going to turn it back till for 30 minutes, dude. You need to make sure it's safe.
Right. Oh, yeah.
So, like, having that ability and getting those two groups together, which, working on that with NERC, and also in Brussels and in Australia, Yanni on my team is helping drive that. But it's a function of making sure that interoperability is good, and how you can use energy storage systems or a BESS, whatever that storage system looks like, to maintain load demand so it doesn't affect the grid significantly. Because what's happening is, because there used to be a lot of, they call it in the grid, load diversity.
Yeah.
Right? Load diversity meant like different things turned on at different times. And it was all running.
I just generate and it all kind of figures itself out.
Yeah. But there's still a natural harmonic, and I'll use an American East Coast example, is there's like a 0.5 hertz or 0.1 hertz natural harmonic that goes from the south to the north and the north to the south based on where the load is and where the generation is. And like the grid, I think of it like an ocean, right? And it's rocking back and forth. But then there's other loads that are causing these distributions. And if you basically drop 1.5 gigawatts off load, it causes a wave.
Yeah, that makes
Right?
sense. Yep.
And it's like an ocean, right?
Yeah.
It's okay. But eventually, if you have too many waves happening at the same time, a rogue wave will happen, right? You have an amplitude effect where it all compounds. And that will be significant for the grid at that time.
Yeah, I think a lot of people think of the grid problem. I would say that people that aren't as intimately involved in the power side of our industry are like, oh, data centers use a lot of power. True. But conversely, as big of a problem, if not a bigger problem, is the time they can't use the power that they were provided in the first place, creating those waves.
Exactly.
And maybe bringing the whole grid down.
That is a distinct possibility.
Yeah.
Hopefully it does not happen. So we can mitigate that. And there's ways to mitigate those waveforms.
And it sounds like DC power topology would help potentially enable other equipment, other devices to be able to help mitigate that.
Yeah, I think it's a symbiotic effect. I think we're still working through how DC exactly will support.
Sure.
But yeah, using, if you meant by battery energy systems, like a DC battery, like there's a lot of technology you can utilize that to support that grid to maintain continuity, because we have to be a good grid citizen, right? Like everybody, the world works based on everybody working the best they can, common trust, and positive intent. And working together to support the whole ecosystem is what matters.
Yeah. On that, I mean, I think that sums up exactly what, while I'm so glad you're involved in open compute and the value you see in bringing everybody together, we're glad that you're bringing the power community more into OCP so we can do more. Finishing up, anything else people should be aware of, or what do you want them to do?
Feed the good wolf, right?
Good wolf.
Right. So everybody's worried about this AI and what it can happen, right? I think we need to focus more and more on the positive aspects of artificial intelligence and the way that it can benefit humanity. Because generally what wins is what you give energy to.
Yeah.
Focusing on the benefits for humanity and doing as much good as possible, like that's what it's about.
I love that. Feed the good wolf.
Yeah.
I really appreciate it.
Yeah,
Thank you for coming to talk to me.
Appreciate it.